This is lesson 3. Today, again, we're going to work on making sure we understand how we have summarized lessons 1 and 2, put it all together, have lots of work time as you guys are given opportunities to try new problems. Please remember that in a rational function, we're talking about ratios. We're dealing with fractions. The numerator houses your x-intercepts, the denominator houses your vertical asymptotes, and we look at the whole function to find the horizontal asymptotes. So as we put that together, again, really what you're doing is you're setting different parts of the function equal to 0, factoring and solving for x, and then remember you always want to state your behavior. So in order to, as we just mentioned, the x-intercepts are found in the numerator. So in order to find those x-intercepts, you set it equal to 0, and then you factor and solve for x. After you're done, you want to make sure that you give your behavior as a cross or a bounce, and you also want to make sure that each of your solutions are presented for you in ordered pairs. Set the denominator separately equal to 0, and that's going to give you the location of your vertical asymptotes. Again, you want to factor and solve. Here, your answers are going to be x equals line, so they get that vertical line. And based on the multiplicity, you're either going to say sign change or no sign change. And then we look at the whole function to find those horizontal asymptotes. So here is a practice problem. Again, what I want to do today is give you guys plenty of opportunities to look over the problem, try it for yourself, ask questions, and make sure by the end of today you understand. So as we're looking at finding the x-intercepts, again, we set the numerator equal to 0. Then we're going to factor. Solve for x. And then write our final answer as a coordinate. This has a multiplicity of 1, therefore it's going to cross. -1 has a multiplicity of 1, therefore it's going to cross. To find the location of your vertical asymptotes. Now we're setting our denominator equal to 0. Solving for x. And again, we want to list each separately with our behavior. Because of that multiplicity of 1, they both have a sign change. We look at the whole function to find the location of the horizontal asymptote. We start by finding the degree of the numerator. This is a quadratic, so that makes it a second degree function. The denominator has 2 x factors, again making that a second degree function. So that fits into rule 2 because the numerator is the same as the degree of the denominator. Then your horizontal asymptote would be the ratio of the leading coefficients. Again, you want to look at the highest powers to find that. Next, we need to determine if that's going to cross or not. So we're going to put 1 in for x, 1 in for y, and solve for x. Now in this situation, it's going to be easier if we put that denominator in factored form because it's going to be easier to solve the algebra once our functions are in factored form. Your first step anytime you're solving for x when you have this fraction is to cross multiply so that we can get rid of that denominator. Again, anything times 1 initiates the same thing, so just clears that fraction and moves it from the denominator over to the other side. What we can see is we have a positive x squared on both sides, so that goes away, leaving us with -x minus 20 equals 6x plus 5. I'm going to get my x's together, so I'll add that x. And then I'm going to subtract the 5. So I get -25 equals 7x. Divide by 7. Now that is going to give me the location of where my graph will cross the horizontal asymptote. So our horizontal asymptote happens when y equals 1, and then we're going to say cross at negative 25/7, comma 1. And here's an image of the graph. Unfortunately, the horizontal asymptote got put in the wrong spot on this image, so it should be when y equals 1, not at 0. And again, we can see that point of negative 25/7, comma 1, where the graph crosses that horizontal asymptote. You can also see the behavior at the X-Intercepts as crossing points, and you can see the behavior near the vertical asymptotes with that sign change. Let's go through a second example. Again, if you're watching this YouTube video, you should be pausing, attempting this question on your own, and then pressing play to check over your answers. For the X-Intercepts, again, we're setting our numerator equal to 0, and we're solving for x. Now, x equals 1, but it has that multiplicity of 2, so when we list that coordinate, it's 1, 0 with a bounce. To find your vertical asymptotes, you're setting your denominator equal to 0. Again, solve for x. Each of those have a multiplicity of 1, so we write x equals negative 3 with a sign change, and x equals 6, sign change. Again, as we're looking at this, we need to look at the overall degree of the function to find that horizontal asymptote. So I have 2 factors in the top because of that multiplicity of 2, and I can count 2 factors in the denominator. Second over second gives me rule 2 again. And again, it's going to be at the ratio of the leading coefficients. So that means my horizontal asymptote happens when y equals negative 2. Again, I'm going to put negative 2 in for y and solve for x. And that's going to give me the location where the graph crosses that horizontal asymptote. As you're doing your multiplication, please remember that x minus 1 squared means that there's 2 of them, x minus 1 times x minus 1, which gives you x squared minus 2x plus 1. So just like before, we're going to start by multiplying by our denominator so it clears our fraction. Make sure you distribute that negative 2 all the way through. Then you're going to distribute that negative 2 all the way through x minus 1 squared. What we notice is that there's a negative 2x squared on both sides, so that cancels each other out. We're going to move the 4x from the left, the right to the left. Okay, again, we're working on our way to get x by itself. We'll move that 36. So we get 2x equals negative 38. And x equals negative 19. Again, that gives us the location where the graph will cross the horizontal asymptote. So we say cross at negative 19, negative 2. And again, here's that graph. We can see that crossing point. We can see that the graph is below the asymptote before we get to that point, and then it becomes above that asymptote as we pass through it. We can see that bounce happening at the x-intercept. And again, we can see those 2 vertical asymptotes represented each with that sign change across the graph. Go ahead and try a third example. Again, if you're watching the YouTube video, you should be pausing, trying the question on your own, and then coming back to check your work. Find those x-intercepts, set your numerator equal to 0. So x equals 1 and negative 3. Again, we want to make sure we always write those as coordinates and list our behavior. With a multiplicity of 1, they each have a cross. Find your vertical asymptotes. You set your denominator equal to 0. Again, now that vertical asymptote in the denominator has a multiplicity of 2. So now we say no sign change. So as we solve for x, we get x equals 0. Again, because of that multiplicity of 2, it corresponds to no sign change. Your horizontal asymptote is based on the behavior. Again, we look at this function. It's a second degree function over a second degree function. So your horizontal asymptote is going to be the ratio of the coefficients. So this fits into rule 2, where y equals 4. Put 4 in for y and solve for x. Again, just like before, your first step is going to be to cross multiply. We're going to distribute that 4 all the way through. There's a 4x squared on both sides. That cancels out, leaving you with 0 on the left. Move the 12 and divide by solve for x. So we divide both sides by 8. So we have 12 over 8, which reduces to 3 over 2. We want to keep the answer exact. So we say y equals 4, and it's going to cross at 1.5, 4. As we put all that on the graph, you can see that your x-intercepts are represented by those 2 points that we found from our numerator. Both were crossing. We can see that vertical asymptote when x equals 0 with the no sign change, so the graph looks like a volcano. And we can see that crossing point of that horizontal asymptote. On this, it's important to recognize that we can also work backwards when we're trying to come up with our function based on our graph. So what I notice about any function is that your x-intercepts are found in the top and your vertical asymptotes are found in the denominator. So when I look at this graph, I see an x-intercept here at 0, 0 with a bounce. So that's going to give me an x squared in my numerator. I have a vertical asymptote when x equals 2. That's going to give me the vertical factor of x minus 2 in my denominator. Adjust the power appropriately since these ends are going with no sign change. That corresponds to a multiplicity of 2, so I want to change that multiplicity to 2 in the denominator. As I look at the overall function, I have a second degree over a second degree. So I know that my horizontal asymptote is going to be the ratio of the coefficients. I can read that directly off the graph by putting in the 3. Again, we want to make sure that our function is adjusted appropriately for the behavior at each of those important components. Again, as we work backwards, it doesn't matter that this graph has an oblique asymptote. We are still going to find the equation of the line the same. So when I look at this function, I see I have an x-intercept at -3 with a cross, an x-intercept at -1 with a cross, and an x-intercept at +3 with a cross. Those are all going to go in my numerator as factors. Then I look at my denominator. My vertical asymptote happens when x equals 0. And again, it has no sign change, which means multiplicity of 2. As I adjust the overall function, I see I have a cubic function over a quadratic function, which will result in an oblique asymptote. I don't need to put that location of that oblique asymptote anywhere in my function. What I would find is if I did the division between those 2 functions, I would be able to locate that oblique asymptote. So it's a result of creating the function, not part of the original function. At this point, you should be able to move on to Schoolology Assignment 3.